My name is Dr. Peter Green. I'm a senior lecturer at the University of Liverpool, and in this tutorial video brought to you from the Centre for Doctoral Training in Distributed Algorithms here at Liverpool, we're going to discuss an introduction to Gaussian process regression. This is a really powerful and expressive machine learning technique that is being used currently by lots of the students who are part of this Centre for Doctoral Training. So today we're going to discuss Gaussian process regression. Gaussian processes can be used for example, classification as well. So I think it's fair to say that for the most part they are used for regression. So that's what we'll focus on today. And I'm going to try to do it in a way that's relatively light on the maths and has a few more pictures than other tutorials you might see. So a good place to start is to briefly review linear regression. So just to be clear, what we're going to do is we've got some inputs x and some what's sometimes called target values y, which we're going to regress against, and we're going to say that we have n points and it's regression. So let's say we have x and y. Here is some data, let's say, and what we'd like to do is essentially fit a model through this data, and if we can, also perform some uncertainty quantification, so perhaps put some confidence bounds on this model's predictions. So with linear regression, what we do is we fit a model which will denote f, and f is a function of the input x, and we're going to say it's equal to a vector of parameters multiplied by some kind, sometimes called a basis of the input x, and it's these parameters, that's what we want to find, that's what we want to estimate from the data. So just as an example, let's say we want to fit some quadratic functions, then we could say that this basis of x is actually equal to a vector equal to x and x squared, and that this theta is now two-dimensional. So we'd say that theta is equal to theta 1, theta 2. So you can see that the model we're trying to fit is really f of x is equal to theta 1x plus theta 2x squared. So we won't go into this in too much more detail, but this is linear regression, and it's linear because although we're non-linear in x here, we're linear in our parameters theta. So that means that we have a closed form solution for theta if we want to minimize the squared distance between the model we're fitting and our data. So that's a very brief example of how we can do some linear regression. Now let's say that you also want to do some uncertainty quantification. Specifically, you're worried about the uncertainty in what theta is, given that our observations of this process, let's say, are a noisy version of what's really happened in reality. So one of the ways you might choose to tackle this is through a Bayesian approach. So a lot of the time what you'll see is the proposal of a noise model. So for example, you might say that your ith observation is equal to the response of the model plus some noise that has corrupted the observation, and you might decide that that noise has been sampled from a Gaussian distribution, let's say with variance sigma squared. You certainly don't have to do that, but that's one thing that you might see quite commonly. And once you've proposed this noise model, that means you can write down your likelihood, probability of seeing each y given theta is by definition now a normal distribution where the argument is y. The mean is the response of the model at that point, which is of course a function of theta. I just haven't written it here, but I've written it here, but I've not written it as a model input for now. And the variance is sigma squared. And then, once you've got your likelihood, then you might also decide to write down a prior, which is actually what we're going to focus on here. So you might decide that you've got a prior over theta, and let's say that that's just some kind of, again, could be a normal distribution with argument theta, which in this case is a two-dimensional vector, and let's just say that it's zero mean and it has, I don't know, the identity covariance matrix. So the prior is completely up to the user. Once you've done all this, you have your prior and your likelihood, then from here you can, if you want to, go on to write down Bayes' theorem and then try and realise a posterior distribution over the parameters theta. But we're not going to do that here. This video isn't really about linear regression. What we're going to do is focus on what this specifying a prior over theta really means. So what we've done is we've restricted ourselves in this example to a quadratic family of functions to fit, and then we've put a Gaussian distribution over theta. So it means that if we generate samples from the prior, then we're essentially proposing different quadratic functions. So what I'm going to do down here is, let's say that this vertical axis is our model output f of x, this horizontal axis is x, and I'm going to go through a two-stage process where I'm going to first of all generate a sample of theta from the prior, and then once I've got that, I'm going to plot how our proposed model varies with x for that particular value of theta, for that particular sample. So if I do that once, I choose a different colour, I sample a value of theta, and then I draw this function, which as we've seen is actually, in this case, some kind of quadratic. And then let's say that I've so far done this once to generate a single line. Let's say we do it again and again, kind of in a loop. Then what we do, if we plot all of the resulting samples, is you'll see that actually what's happening is we're proposing a set of different models. Like I say, we've limited them to be quadratic in this particular example, so they would look a bit like this. The point I'm trying to make is graphically, when you specify this prior, rather than thinking of it as a distribution over the parameter theta, really you can think of it as a kind of probability distribution over these different lines, essentially, these different candidate models that we're proposing. And then, loosely speaking, let's say that we actually get some data that looks perhaps a bit like this. Then if we were to go on and sample from the posterior, the probability of theta given the data that we've witnessed, which is the crosses in this case, the red crosses, if we were to sample from that, so I'm going to colour this in green, then we'd end up with a family of models that are closer to the data and more plausible given the red crosses, given the data that we've seen. So the point I'm trying to make here is that we shouldn't think about this as necessarily as a prior over theta, really it's a prior over the possible models that you could potentially fit to our data. And in this case, like I say, we've actually restricted ourselves to just this quadratic family of models. So now we're going to say, well, rather than this two-step process where we generate samples from theta and then generate samples of f, why don't we just generate samples of f directly? Because ultimately that's what we want to do, is we want to propose these different lines, essentially. So what I'm going to do is define a bold f as being, so let's say that's bold, the vector of f's evaluated all of our training inputs. So it's f evaluated at x1 up until f evaluated at x capital N, and we'll stick with the notation of having column vectors as the default. So like I say, rather than proposing thetas and then proposing f's, let's just try proposing f's directly, because ultimately that's what we want to do. So I'm going to define a probability distribution over this bold f. So it's a multivariate, in this case Gaussian. The argument is this vector f, and for now let's say that it's got a vector of zeros as the mean and a covariance matrix k that we can decide, we can choose. And so this is often referred to in the literature as a prior over functions, which can, I think, when you read it for the first time, be a little bit confusing. But like I say, essentially all we're doing is we're just going to propose this a prior over these different potential models directly, rather than specifying a prior over theta and then seeing what effect that has on f. And our choice of the covariance matrix k dictates what these potential models that we're going to have might look like. So if k was just the identity matrix, then you can imagine that, so if I plot x against f, so I'm going to draw a line here, but what it really is it's f evaluated over x1 to xn. If k was the identity matrix, then essentially what we're proposing is noise, each potential model. So I'll switch to a different colour. I'll go back to blue. Would look a bit like this, and by definition, so there's one, there's another one, there's another one, and by definition, f at, let's say, xi and f at xj will not be correlated, because this covariance matrix is identity. However, if we start to introduce correlations in this covariance matrix, then you get some more interesting stuff. So a classic way to do this is to specify this covariance matrix using something called, so it's always specified with something called a kernel. So when people are talking about Gaussian process kernels, they're usually referring to an equation that's used to formulate this covariance matrix. And we're going to use, like I say, a kind of classic example called the squared exponential kernel. Basically, what it comes down to, so I'll stay with blue, is that the ijth element of the covariance matrix is equal to an exponential. So it looks a bit like a Gaussian. It's got a kind of Gaussian shape. I'm going to say minus 1 over 2. I'm going to put in a parameter, L squared, which we'll deal with shortly. And then here I've just got xi minus xj squared. So what does this really mean? Well, if we look at the kind of, let's say that this is K, this is our covariance matrix, and these are different elements within it. Okay, well, all these diagonal elements will be equal to 1. So yeah, there's another row there. The closer xi is to xj, the higher the value of these elements will be. And then gradually, as let's say the distance between xi and xj increases, then their correlation will reduce. So we'd expect in our covariance matrix, for example, that this element is going to be larger than the value of this element. So moving back to the pictures, what this actually means is it's inducing smoothness, because it means that points that are close to each other on the x-axis are more correlated than points that are further away. So in reality, what this does is it ends up, let's say, in the proposal of some now relatively smooth functions. And we dictate this smoothness using L. So if L was even larger, and as I say, we'll discuss how we choose L a bit later. But if L was larger, then what we're doing is we're introducing more correlation between x values that are far apart. And so we end up producing kind of smoother function values. So let's say that is for large L. And then if we go down here and we think about what happens if we have small l, then it's going to look a little bit more like just the kind of noisy case where k was equal to the identity matrix. So that's small l. And so this is how we can now propose different models without actually having to specify. First of all, we don't have to specify a model structure. So if you recall, for our linear regression example, you do have to specify this. And in our case, we specified this basis function that gave us a quadratic model for f. But that restricts us from that point onwards to only being able to fit something from this quadratic family to our data. So it's sometimes called parametric regression because we're limited to that parametric family. Whereas if we decide that we're going to drop our use of theta and actually just propose f directly, so this is still our prior, and you can see we're no longer actually limited to a specific parametric family of functions. So for this reason, Gaussian process regression is sometimes called non-parametric regression. So that really is the kind of key conceptual difference moving from a linear regression, where it's parametric, to Gaussian process regression, which is non-parametric. Okay, so now we've defined our prior. Let's focus on what we really want to know is that after we've seen our data, then in response to a new input, which I'm going to write as an x star, that let's say isn't necessarily in the training data, then what will be the value of our model at that input location? So f of x star, which I'm actually just going to write as an f star. So the first thing to note is that we can still specify a prior over what our function values could take over x star. Because if we go back up to here, by defining this kernel, we've essentially described the rules that we can use to construct a prior over any values of x. So specifically, what I mean by that is we can now write a probability distribution. So again, like I say, it's the prior over now, let's say, a concatenation of our vector f. So remember, this is f evaluated from x1 to xn, and now f star, which is f evaluated at x star. And we follow the rule that we've specified when we defined our kernel. So the prior over the concatenation of f and f star has, obviously, as an argument, we have this n by 1 vector and this scalar concatenated together. The mean of this is, again, a vector of zeros, only noticing now that this is now a n plus 1 vector of zeros, because we have n and a scalar here. And then we've got our covariance matrix. So we still have capital K here. So that's the covariance matrix that we'd already defined over bold F. And then we've got these extra terms, which I'm going to write as a K star transposed. And this is going to be a K star star, using the usual notation. So this is an n by n matrix, and this is n by 1, so therefore this is 1 by n, and again this is a scalar. So what are these? Well, remember that our prior is just defined using the kernel. So now we've introduced this new, this f star that's evaluated at x star, then it means that each element of this is the kernel. Now, so let's say the ith element of this vector is the kernel evaluated at xi and x star. So we're essentially following exactly the same rules that we defined when we said that we were going to use this kernel to describe correlations between different inputs. The fact that we've introduced a new input, x star, doesn't change anything. It just means we expand this covariance matrix, I guess, by one element, by including this vector that describes the correlations between each of our training inputs and our new input, x star. That's the same vector transposed. And then here we've got the kernel evaluated at x star, which, as in this particular case, as we saw before, is equal to 1. Because remember, when we defined the kernel in this way, we said it led to 1s on the diagonal of this covariance matrix. So now we've expanded it by one element. We just need another 1 here, so it's still 1s all on the diagonal. So before we think about what this value of f star could take, the first thing we need to note is that because we've already defined the kernel, we can include this in our kind of prior now over f and f star. Now, a nice thing about Gaussian distributions is that if we have this multivariate Gaussian, then 1, all of the conditional distributions from this are Gaussian, and 2, we have well-known closed form expressions for what they are. So applying that to this context, what it means is that we can write the probability of f star given f, and that will also be a Gaussian, and like I say, we can then rely on some closed form expressions that are well known for Gaussian distributions to show that the mean of this particular distribution is this k star vector transposed the inverse of k multiplied by this vector f, and then the variance is going to be our k star star, which is 1, but only in this particular case, it's not 1 in general, minus k star transposed k to the minus 1 k star. So I'm not going to derive that. You can get it from closed form solutions from lots of different textbooks. But the point is that this conditional distribution is also Gaussian. So it almost looks as though we have what we need. We have probability of f star given f. But you have to remember that f isn't actually what we observe. What we observe is y. And we believe that y, if we go all the way back up here, we have this noise model. We believe that what we actually observe is a noise corrupted version of this true function f, and we don't know what the true function f actually is. So what we actually need to do is we need to know the probability distribution over f star given y. That's what we actually want, because y is what we really observe. We never actually observe this bold f. The true function is hidden to us. And you can compute this by evaluating the integral of probability of f star given f multiplied by the probability of f given y all over df. So what we're doing here is we're marginalising over f, because that's the thing that we don't know. We never observe f, we only ever observe y. So if we can evaluate this integral, then we get what we really want, which is probability of f star given y. So fortunately, we already have this because we've derived it here. So we know that that's a Gaussian distribution. So what we need to do now is get an expression for the probability of f given y. So what I'm going to do here is write down Bayes' theorem. So we know the probability of f given y is proportional to probability of y given f multiplied by the probability of f. Now we already know this because we defined it ourselves. We know that this is a normal distribution that is zero mean and has covariance matrix capital K. As for this second term, recall the noise model, which, as I say, we specified at the start of the video when we were talking about linear regression. We hypothesized the model that the ith observation is actually equal to the response of our model evaluated at xi plus some Gaussian noise. And that noise is zero mean and has variance sigma squared. So that implies that, again, it's a model that a noise model that we've hypothesized. If we choose to believe it, then it implies that the probability of witnessing observations y given f is a normal distribution, argument y. The mean is this vector of f's. So again, this is f evaluated from x1 to xn. So here we're talking about y at the input points x1 to xn. And its covariance matrix will just be the identity matrix multiplied by sigma squared, i.e. the noise variance. So once we have both of those, so this is here, then we won't go into it now because we won't learn much from doing it, but these are both Gaussian distributions. You can evaluate Bayes' theorem in closed form, and you can get a closed form solution for probability of f given y, and this is also Gaussian. And finally, because this is Gaussian and this is Gaussian, then we are also able to evaluate this integral. Like I say, we won't go into it and derive everything in this particular video, mostly because these are all just closed form expressions for Gaussian distributions that, like I say, you can get out of any textbook. So going through it line by line doesn't necessarily teach us much extra stuff, although it is an interesting exercise to do. So once we have evaluated that integral, what we eventually end up with, which I'll write just for the sake of completeness, is the probability of f star given our observations y is a Gaussian distribution. The argument is f star, and it's got a mean and a variance, which I'm going to write as a mu star and sigma star squared, respectively, where mu star turns out, like I say, once you've worked through all the maths, turns out to be equal to this k star vector transposed, our k matrix, which was defined when we defined our kernel, plus what we sometimes call a ridge, the identity matrix times sigma squared, multiplied, this is inverted, multiplied by y, so that's our vector of observations, and then the variance sigma star squared is equal to k star star. Defined earlier in the video, we've got this k star matrix vector, again transposed. We've got this k plus identity sigma squared inverted again, and then we have our k star vector to finish it off. And so this is what we really want, is now we are able to evaluate when we get a new input x star, we have a probability distribution over what f star could be. It's Gaussian, we have an closed form expression for its mean and variance, and so because we have this information, then we're able to quantify the uncertainty in what f star could be as well. So for example, you might put 3 standard deviation confidence bounds on your prediction, which you would derive from this expression here. So that is nearly that. The only thing that we haven't addressed is if we go all the way back to when we defined our prior, is we said that we defined a kernel, and it had this L in there, which is actually called a length scale. And it's this L that determines essentially what these prior functions really look like. And in this case, with a squared exponential, we can think of it as determining how smooth these prior functions are. So the final thing we need to do, or need to discuss before you can go and implement a basic Gaussian process, is how we go about finding that length scale L, as you can think of that as a kind of parameter that does need to be tuned. So the most common approach for choosing, in this example, the length scale is maximum likelihood, where what we try to do is find the length scale that maximizes the probability of witnessing our observations y. So now I'm going to write this conditional on, like I say, in this particular case, it's an L, our length scale. So we want to find the length scale that maximizes the probability that we would have witnessed the data y. And we can get this distribution by, again, marginalizing, where we have probability of y given f, which we've already defined earlier in the video using our noise model, and probability of f given L over df. This is again just the prior over f. The only difference is that now I've specifically noted that it is conditional on L, because we're talking about finding the maximum likelihood estimate of L. Again, these are both Gaussian distributions, so we can evaluate this integral relatively easily to find that it's equal to a normal distribution, argument y, mean 0, and it has covariance matrix k plus I sigma squared, where it is the k here, which is a function of the length scale. Because remember, the elements of k are determined by our kernel, and our kernel contains L. So the most common approach would be, specifically to avoid numerical issues, is we try and pick the L that maximizes log probability of winners in the data given L, and we try to maximize this. We don't have a closed form solution for it, so most typically that's tackled with gradient descent, for example. So that ends this introduction. Again, the key points here is that rather than with standard, let's say, linear regression approaches, where we propose a prior over some parameters theta, and we fix our models to belong, our potential models to all belong to the same parametric family, with a Gaussian process we actually specify the prior directly over, in this case, the vector f. If we also decide to use a Gaussian noise model, then what we end up with is closed form solutions for the mean and variance of our model at new input x star. Finally, we noted that there are some things you need to tune during this process. In this particular case, we had a length scale in the squared exponential kernel, and typically these are tuned using a maximum likelihood approach, where again, because everything is Gaussian, basically we end up with a closed form solution for the log likelihood. Note that there can be other parameters here as well, so here we just have a single length scale, but you could also include the noise variance if this is unknown, and any other parameters that you include in the kernel. And so that concludes the introduction to Gaussian process regression.